Hello, my name is Richard Harrison from the University of Cambridge, and it's my pleasure to present this work on behalf of Peter Robinson and my co-workers Suzanne McEnroe, Carl Fabian, Florian Heidelbach and Mike Jackson. Now, it was an absolute privilege to work with Peter over the last 20 years on the magnetic properties of the ilmenite hematite system. And I'm going to present today some of the last work that Peter was working on before he sadly passed away. And it's work that I think really epitomizes the way that Peter would approach his science. And it's impossible for me to do this justice in 12 minutes, but I'm going to try my best. So, our adventures at the nanoscale with Peter began in around 2002 with the discovery of lamellar magnetism as an explanation for the strong and stable magnetic remnants carried by nanoscale intergrowths of ilmenite and hematite. And these intergrowths, as you can see here from this TEM micrograph, vary in length scale. So this is an ilmenite host containing hematite lamellae in this case, and those hematite lamellae change in size and decrease all the way down to the unit cell scale. And what Peter and I and Suzanne and Rob Hargraves discovered is that the ilmenite, the presence of these nanoscale exsolution lamellae generates a magnetization which can explain that strong and stable remnants. And that's illustrated here. So we're seeing here a snapshot of a computer simulation showing a hematite host, in this case, with an ilmenite lamella inside it. Now the hematite is antiferromagnetic, has a magnetically ordered structure consisting of equal and opposite left and right oriented spins, which would normally cancel each other out almost exactly. But when you place an ilmenite lamella into this hematite host, you generate a net imbalance of spins. There are slightly more spins pointing to the left here than there are to the right. And those uncompensated spins are carried by the interface layers here, which we call contact layers, which contain a mixture of Fe2+ and Fe3+. So placing a paramagnetic ilmenite lamella into an antiferromagnetic hematite host generates a net magnetization associated with these uncompensated interface spins, what we call a lamellar moment. Now, a profound implication of this theory was that the net remnants of these intergrowths depends on the physical placement of the ilmenite lamellae within the hematite host structure. As you can see from this comparison here, here's two ilmenite lamellae sitting in a hematite host, and they've been placed in such a way that the net spins here both point in the same direction. If you displace the ilmenite lamella here, however, by a single atomic layer upwards, then the net magnetization that it carries points in the opposite direction. And so there are two types of ilmenite lamella here, and the populations of these two types and the bias between them generated by the magnetic field that was present as these exsolution textures were forming is what encodes the natural remnants, okay? So the natural remnants is controlled by the chemical microstructure and is encoded by the physical placement of those lamellae. Now, the next major event in our adventure was the discovery in 2007 of giant exchange bias, and this was work done by Suzanne McEnroe and appearing in Nature Nanotechnology. Now, if you do a magnetic hysteresis loop of one of these intergrowths at room temperature, where only the hematite is magnetic, then what you get is a rather conventional looking hysteresis loop, okay? A normal looking hysteresis loop that's centered around the origin. However, if you take that sample, place it in a very strong magnetic field, and cool it down in that field until you get below 55 Kelvin, that's the temperature at which the ilmenite also becomes antiferromagnetically ordered. Then if you do that, something rather dramatic happens. The hysteresis loop suddenly shifts by over a Tesla to one side. And it's this shift of hysteresis loop that we call exchange bias. So here's the origin now. Now, to illustrate that shift, the easiest way to do is to take the difference between the upper and the lower branches of the hysteresis loop, and that gives you this signal here. And normally, this signal would be centered around the origin, but here you can see it's shifted off to the left by over a Tesla. And that's a really enormous field, which led Suzanne to name this sample the OMG sample, which I think is what she shouted when she first saw this happening in the magnetometer at the Institute for Rock Magnetism. Now, what's causing that shift? That shift is caused fundamentally by a exchange interaction between the hematite spins and the ilmenite spins across the interface, the lamellar interfaces. And that's illustrated very nicely here in this simulation. So again, we have a hematite host and an ilmenite lamellae. Just highlighting here the core of that ilmenite lamella here, we can see the spins are antiferromagnetically coupled. So spins are pointing down, up, down, up, down. But there are more down-pointing spins than up-pointing spins. And so that ilmenite lamella itself also now carries a magnetization, a net moment, which is pointing downwards in this case. The contact layers surrounding that ilmenite carry the lamella moment, called MH here, and that's pointing in this direction. You can see following these contact layer spins. And the interaction between the contact layers and the ilmenite spins here is such that these would like to be as anti-parallel to each other as possible. Okay, it's a net negative coupling. So that means that we're in a low energy situation here where the component of these hematite spins is pointing anti-parallel to the ilmenite spins. Now, to reverse the hematite spins requires us to violate that exchange coupling. The ilmenite spins do not change as you change the magnetic field. They're very strongly fixed in place by the strong intrinsic anisotropy of Fe2+. But as we apply a negative field to try and reverse the hematite spins, they have to overcome that exchange coupling. And that violating that exchange coupling requires us to apply a much larger negative field than we might otherwise need to. And it's that generates this shift of the hysteresis loop. Now, the next major part of this story came with work by Carl Fabian in 2008, and then followed by work by Suzanne and Peter in 2016 and 2017. The major discovery here was that this exchange bias phenomenon does not only occur when you apply a strong field during cooling, it actually also occurs, and even more strongly, when you do a zero field cooling. And that the exchange bias you observe is controlled by the natural remnants of the ilmenite-hematite intergrowth. So the key observations, what they found here, is first of all, that if you cool in a zero field, so what we call NRM cooling, then this exchange bias occurs very strongly, but you get a bimodal exchange bias. The hysteresis shifts both towards the negative direction, as we saw earlier, but also into the positive direction as well. So two exchange bias signals, and the relative heights of these exchange bias signals depends very much on the orientation of the NRM placed into the magnetometer. So here we can see that the NRM has a component in the negative direction in the magnetometer, and it's the positive exchange bias signal which is dominant. Compare that with here, where we now have the NRM much more strongly aligned with the positive direction of the magnetometer, and it's the negative exchange bias signal which is much more dominant. So the NRM controls the exchange bias, and the relative sizes of these two signals depends on the orientation of the NRM in the magnetometer. And this is a remarkable result with profound implications. First of all, it really proves the lamellar magnetism hypothesis. Because exchange bias is inherently an interface phenomenon, if the NRM is controlling exchange bias, it means the natural remnants of these samples must be also carried by those interface moments, which is a kind of a proof of the lamellar concept. And the fact that the NRM, the evidence of where the NRM is pointing is evident in these hysteresis loops, which are measured in fields of up to 5 Tesla here, demonstrates that that NRM is tied and locked into the chemical microstructure of these things. So it's a really important, profound result. And it's one, of course, that Peter really wanted to understand at a fundamental level. And the work that we've been working on really epitomizes Peter's approach to this. To understand what's going on here, we have to start at the atomic scale. So Peter starts at the atomic scale with individual layers of cations. This is a hematite layer containing the ordered hematite spins. We have a contact layer here containing Fe2+ and Fe3+ with their ordered spins. We have a titanium layer in the ilmenite, and we have the Fe2+ layer in the ilmenite here with its ordered spins. Now, from these little hexagonal building blocks, what you can do is build up a full single layer of the structure. So to build a layer, to find a particular diameter, to build this lamella, so particular radius, and from these hexagonal building blocks, build up a single layer. From those single layers, we can then stack those on top of each other in order to generate essentially a three-dimensional model of one of these ilmenite lamella within the hematite host. And these have been designed to capture the thickness and the aspect ratio of the ilmenite lamellae, which are observed in transmission electron microscopy, and to sort of model different growth formation mechanisms to produce these tapered ilmenite structures. Now, from that individual models, then add in the details of the spins. So where the hematite spins are pointing, where the ilmenite spins are pointing, where frustration is happening at various points within these lamellae, where the spins are having competing interactions, telling them to point in different directions. So from the radius of these layers that we've stacked up, and from the spin arrangement that we know from the modeling that we've done, it's possible to calculate by hand the total magnetic moment associated with the lamella moments at the interfaces, and the total magnetic moment associated with the ilmenite part of these lamellae. Now, from those individual models, you can start thinking about a rock which contains grains oriented in lots of different directions. And for each of those, you have the natural remnants that was acquired in the field, in the Earth's magnetic field, over 1 billion years. Okay, and knowing where the hematite spins are pointing and where the corresponding ilmenite spins are pointing, you can then generate a model of how those might be arranged. So what's shown here are the hematite spins, the corresponding ilmenite moments calculated from all of these models, how they are arranged in the magnetometer. And you can see here you've got lots of these ilmenite spins here, which are pointing over to the right here, which are the dominant ones, and you've got ilmenite spins here, which are pointing over to the left, which are not the dominant ones. Okay, much smaller signal. And placing a rock like this into the magnetometer with its NRM pointing in this direction is going to yield an exchange bias, which is dominantly in the positive field direction. Whereas here you're going to get an exchange bias in the negative direction, which is lower in magnitude. So through these models and calculating the ilmenite spins that are present relative to the hematite spins, you can make a prediction of the relative magnitudes of the exchange bias signals that we see as a function of orientation of the NRM in the instrument. Now you can do that in 2 dimensions, but that's not good enough for Peter. He wanted a 3-dimensional model of this. So by distributing these individual ilmenite lamellae, which has been calculated into a 3-dimensional model, and then even that's not then enough, because you then have to account for the fact that in the actual rock there's a texture, and these ilmenite lamellae are not distributed entirely at random. There's a distinct texture here measured by EBSD by Florian Heidelbach, and using that information, feeding that into the 3-dimensional model, and adding that to the quantitative models of these individual lamellae, you can then make a final prediction of how these exchange bias signals vary as a function of how the NRM is placed into the instrument. So these are these various lines here which incorporate that textural information, and the data points here are coming from the hysteresis loops, the measurements of those relative sizes of those exchange bias signals. And we get a pretty good match. A couple of outliers here, but this is a pretty good model. So I hope, the details are rather complex of this, but I hope you can give a flavour of the way Peter, the sort of rigour and the way in which Peter did this science. It was an enormous privilege to work with him. It's been a great adventure, and thank you, Peter, and I hope there's lots more to discover in this system.